All right, today we're going to look at the parallel axis theorem for rigid objects. So this is a pretty cool thing that we can use for objects that we can't yet find their moment of inertia about any point. We only kind of have the basics. We only know what their moment of inertia about their center of mass is. So first thing you need to know is the center of mass moment of inertia. So the example we're going to do today is a ring, and the center of mass moment of inertia for a ring is mr squared. And we want to figure out what is the moment of inertia of the ring about its edge. So if I hang it on a very edge corner and let it rotate around that, what's that moment of inertia? You also need to have a new axis that is parallel to the original one. So for instance, my axis that's mr squared is right through here, so my new axis has to be right through here. I can't say this axis and then have another axis that maybe goes like this. The two axes have to be parallel, as the name suggests. This is the theorem. It says I is equal to ICM plus MD squared, where D is going to be our distance from the center of mass to our new point. Okay, so you just need to know what that distance is. So for instance here, this was our old center of mass. So this is our distance, and our distance is R in our case. All right. So let's apply it. So our new I value is going to be the center of mass moment of inertia, so mr squared, plus this md, and in our case, our new d value, the distance from the center of mass to our new point, is r squared. Okay. And you'll notice that I just get 2mr squared is my new I value. And that makes sense because we moved mass further away from the center, and so we've increased the moment of inertia just by how we've distributed that mass. Now, something to keep in mind is when does this theorem isn't needed for, say, a point mass? And so in this example, maybe I picked a point maybe over here, a distance of, say, 3r away. In this case, considering this a point mass instead of doing the parallel axis theorem results in a value of like 1.11. So it's not terribly different than just using 1 mr squared. So there's only a 10% error, or 11% I guess, error when using just 3r. So as long as that r is significant, or this d value is significantly larger than the size of your object, you can use that point mass value. You don't have to do the parallel axis theorem with a whatever type of object you have.